Hey everyone, and welcome to round 2 of rational functions. We're going to try to graph this rational function and find all of its special points and asymptotes. So let's just jump right into it. So the first thing I want to do is find my horizontal and slant asymptotes. I do that by comparing the degree of the numerator to the degree of the denominator. The degree of the numerator is 3 here, and the degree of the denominator is 4, so this function is bottom heavy, and I know that the horizontal asymptote for this function is y is equal to 0. Now let's try to find our y-intercept. This is pretty straightforward. All I need to do is plug in 0 wherever I see x in my rational function, and solve for the value of the function. Doing a little bit of math, boiling all that down, I get a y-intercept of -5/4. So the next thing I want to do is factor both the numerator and the denominator. Now, these are larger polynomials, so I can't just use, say, the quadratic formula or factoring by parentheses. Instead, I have to use long division, kind of like what we did in the polynomial episode. So after going through all of that long division, I get this factorization for the top and this factorization for the bottom. I'm going to pause here for a second just to show how this polynomial long division works. So, on to finding our vertical asymptotes and our holes. We should have vertical asymptotes at x is equal to -1, x is equal to 2, and x is equal to -3. These are the x values for where our denominator is equal to 0. But wait! We see that we have a common factor between the numerator and the denominator, x plus 1. Therefore, that vertical asymptote at x is equal to -1 is actually a hole, because it cancels again with the numerator. So the last thing I do is find my x-intercepts. Since we've already factored the numerator, this is pretty straightforward. It's wherever the numerator is equal to 0 that I will have a 0 for the function. So since we've already factored it, those zeros will fall right out of that factorization. So we'll have zeros at x is equal to -5 and x is equal to 3. We would have had a 0 at x is equal to -1, but as we just found, there's actually a hole at that point. Now it's time to graph the function. The first thing I like to do is graph my horizontal and vertical asymptotes. This gives me a bit of structure to work with in terms of graphing the rest of the function. So I have a vertical asymptote at x is equal to 2 and x is equal to -3, and I have a horizontal asymptote at y is equal to 0. Now I can just plot my other points. I can plot my zeros at -5, 0 and 3, 0, as well as my y-intercept at 0, -5/4. Now notice that my x-intercepts actually lie on my horizontal asymptote. Normally we think of a horizontal asymptote as something that the function doesn't cross, but it's okay for the function to cross it in the short term. It's in the long-term end behavior that it will always approach that value, but never cross the horizontal asymptote. The last thing I want to do is plot the location of my hole. Now the y value for the hole, where x is equal to -1, is going to be the value the function would be if we neglected the x plus 1 factors in both the numerator and the denominator and plugged in -1 everywhere else for x. This gives us this point here. So now, how do I actually graph this function? Well, I need to look at the symmetries and the important values that these points give me. So for instance, the function has a factor in the denominator, which is x minus 2 squared. This means that the function is going to be even across that boundary, x is equal to 2. Same thing goes for the factor x plus 3. At that vertical asymptote, x is equal to -3, the function is going to have odd symmetry across that boundary because the power above x plus 3 is just 1. It's odd. Otherwise, the function needs to pass through all of those other points. So we basically have two different ways that this function could look, either this or this. But which one is it? Well, if we look at the upper function here, that one actually crosses the x-axis more times than is allowed by what we know about our function. It's the lower one that only passes across the x-axis twice that's the function that we want to use and is actually the graph of this function. Now, we could plot other points to verify this. We could plot points that are less than -3 or greater than 2 to see what's going on towards the end behavior, whether the value of the function is positive or negative. We could also plot some points between -3 and 2 to see if the function is positive or negative along that domain as well. But because we used what we knew about the function and some logic, we can actually plot this function without using any additional information. Now, this is a reasonable approximation of what this function actually looks like. In order to plot it super accurately, we would need to plot a whole lot more points, but in general, to see what the shape of the function is and how it evolves over various values of x, we've plotted reasonably well. If you have any questions, leave them in the comments below, along with any suggestions as usual for things you'd like to see in future episodes of How'd You Get That. Hit that like button, subscribe, and hit that notification bell so you never miss another math physical problem solving tutorial. Thanks so much for watching, and I'll see ya in the next problem.